When after 1 minute we can start.
Yes, sir.
Exactly at 3 we will start.
Yes, sir. I guess I can start now. It's 3.
We can wait for a couple more minutes.
Yeah, 1 or 2 minutes you can wait. Then
Yes,
yeah.
sure, sir.
It's going YouTube live.
Oh.
Yeah.
Yeah.
I'm going to share the lecture at the end of the session.
Yeah, but don't publish it on the web.
No.
Many of the images are not credited. Okay, they are not mine. So many of the images are not credited and so on. So I don't want this to be a public lecture. I mean, it's a public lecture, but it's not a publicly available recorded lecture.
Yeah. Also, somewhere in between you can say.
No, I will say
Not when it's been taken from someone the
Yeah, upfront I will say it usually. So
that's enough. No difference between the times. Madam, we can start, I think. Yeah. Please start.
Yes, sir. A very good afternoon to one and all present here. So today we all have joined here for the Distinguished Guest Lecture Series, and today's resource person is Dr. D. Manjunath. And the Distinguished Guest Lecture is organized by Board for IT Education Standards in association with Dayanand Sagar University. First of all, I'd like to extend a warm welcome to today's speaker, Professor D. Manjunath, Professor of Electrical Engineering, Indian Institute of Technology, Bombay, our Honorable Vice Chancellor of Dayanand Sagar University, Dr. K.N.B. Murthy, respected Dean, Dr. A. Srinivas, the faculty from Dayanand Sagar University and Dayanand Sagar Autonomous Technological and Dayanand Sagar Colleges. And let me introduce our speaker. Dr. D. Manjunath received his bachelor's from Mysore University, MS from IIT Madras, PhD from Rensselaer Polytechnic Institute, Troy, New York, and he has worked in corporate R&D Center of General Electric in Schenectady, New York, and also he was a visiting faculty in the Computer and Information Science Department of University Delaware and postdoctoral fellow in the Computer Science Department of the University of Toronto. He has worked in IIT Kanpur and currently he is working at IIT Bombay. His research interests include computer and communication network protocols, system and algorithm performance, modeling, queuing theory, and simulation stochastic systems. He has authored 2 books and more than 90 research papers in journals and conferences. Also, his inventions include technique for measuring response times in local area network as an invention assigned to the University of Toronto for possible patenting and commercial exploitation. Also, there are some software developed like Remote NAT for Always Best Connected Service, Aerosmith QNAT for queuing network analysis tool. Sir, we are eager to hear you about today's distinguished lecture series. on Wi-Fi, looking back and looking forward. I welcome all faculties, my colleagues, and dear students for the distinguished lecture on Wi-Fi, looking back and looking forward. Over to you, sir.
Yeah, thank you very much for the invitation. And yeah, it's a pleasure speaking at this venue. Yeah, so I took us, I have a little bit of an interest in always looking back. So some kind of a interest in how things evolved and or uh, how things start. And it is in that spirit that I decided to give you a little bit of the history of Wi-Fi, how it started, because this also gives you, I believe, some glimpse. I mean, some of these events I was sort of partly involved, and I followed it very closely because of my involvement. So I sort of have some first-hand experience from a long time ago, of course, about how standards happen, and things have become a lot harder now, but they weren't any less hard before. So some I'll give you a little bit of an insight into that, and then also about how technology evolves. I mean, what starts off as something that has a very simple utilitarian objective, without knowing, before we know it, has essentially manifested itself into this massive infrastructure of what we call a Wi-Fi networks. So that's the looking back and looking forward part. So treat this more as a story and rather than as some spectacular insights into any technology. Story of how technology evolves rather than the details of the technology. I'm not going into too many details, although, I mean, if anybody is interested, I'll be happy to elaborate on many of the aspects. Yeah. Okay, at the outset, many of the pictures and some of these things have been taken from sources, and I have not always attributed them. Many of these are not mine. A couple of them are mine, but many of them are not mine. So this is not meant to be recorded and given to everybody. So this is more a lecture only for this audience, and it is not meant to be a live lecture. So pardon that. I did not have time to sort of sit down and do all of that. These are material that I had collected once, and I just put them together for this talk. Yeah, so the outline of this talk is this. So I'll give you the role of what is called the medium access control in the networking stack. So Wi-Fi is a medium access control protocol, and I'll tell you where it sits in this networking stack. And Wi-Fi is what is called a multiple access protocol or a random access protocol. These are two separate notions. Multiple access is one scheme where there is a common channel and multiple node pairs, receiver transmitter pairs, want to use this channel in some manner. Random access is a particular version of multiple access where there is no coordination. So there is some kind of a distributed coordination where there is so the inherent randomness of the attempt sequence is exploited to keep the protocol very simple. So I'll give you a historical overview of both of those, and then give you a description of the original CSMACA. This is the name of the protocol, or the 802.11 protocol, which was the genesis of the Wi-Fi interfaces. Then that will give you insight into what are the performance bottlenecks. I mean, why should we be worried about using Wi-Fi as it was originally designed in today's networks? Where do the bottlenecks occur? And then based on those bottlenecks, I will tell you how some enhancement were built into some of the early extensions of the basic 802.11. One of them is 802.11n. And then I'm going to tell you a little bit about how things are evolving towards what is called Wi-Fi 6. So now the emerging standard is called 802.11ax. Another name for this is Wi-Fi 6. So based on this, people have started giving backward names, in the sense that after these standards had gotten some names, now they are being sort of retroactively called 802.11, Wi-Fi 5, Wi-Fi 4, and so on. Okay, so just to remind you, Wi-Fi is a link layer protocol. I mean, I'm assuming that many of you are familiar with the networking stack. It's the standard that specifies Wi-Fi includes the scheme of encoding. So essentially what this means is that how are the bits represented on the radio channel, on the wireless channel. Okay, so the waveforms associated with representing bits. It also determines what is called framing. Okay, you have a sequence of bits that are getting transmitted, and you want to be able to determine when a packet begins and when a packet ends. So this is what is called framing. So demarcate packets and then also provide what is called link layer addressing. So if there is a node, for example, your cell phone, which has a Wi-Fi interface, is transmitting something on the air using the Wi-Fi protocol, the access point in your house has to pick up that channel, pick up that signal. It could also be that your laptop, through to which you could be tethered, can also be picking up the channel, picking up the signals. So you have to ensure that it is only the access point that picks up your packets and nobody else. So that is essentially what is called MAC layer addressing. It also provides what is called error detection. It knows so that you can determine good packets from bad packets. It also, then there is this notion of an acknowledgement. So when a sender, when a receiver receives a packet, that packet is acknowledged by the receiver. And if this acknowledgement is not received in time by the transmitter or the sender, a retransmission is triggered. So Wi-Fi is what is called a distributed medium access control protocol that arbitrates among contending users. Arbitrate means, so when more than one person or one node wants to access the channel at any given time, so there is a mechanism built into this 802.11 to determine who gets to go first. Okay, that's called arbitration. It's exactly the same idea. It just arbitrates among multiple contending users. It is a descendant of something called the Aloha Protocol, which is older than which is approximately as old as probably my eldest brother, if I had a very old brother. Okay, so it's from the 1960s, and Aloha gave way to something called CSMACD or the Ethernet, which many of you are familiar with, as an interface. But the original Ethernet is nothing like what the Ethernet is today. Okay, so but there is some interesting features to that. I'll again quickly glance over that and tell you a little bit about the standards battles associated with that. Okay, so let's begin with Aloha. Aloha is a very simple protocol. The basic idea is you just transmit and pray. Okay, so the idea is if you want to send a packet to somebody, there's only one channel available. There are multiple nodes who want to talk to each other over this channel. At any time, only one transmission can be active at any time. If more than two people transmit simultaneously, then the transmissions are lost. Okay, so the simple protocol is what I'll call transmit and pray. You just transmit and hope that the intended receiver receives this particular packet. Okay, how the intended receiver is supposed to know that it is a packet meant for him is exactly like what we do in Wi-Fi. There's an MAC address and so on. All of that, let's assume, is built into it. But I'm interested in only at the protocol level. So I just transmit and hope that the receiver receives this packet. Why is this useful? Or where is this applicable? It is applicable in scenarios where what we call the propagation delay is very, very large. So if I transmit something, or if I'm hearing something on the channel now, that signal actually originated a long time ago. So taking some action now based on a signal or based on an activity that happened a long time ago is meaningless. So there is no other way but to use this protocol that I'll call transmit and pray protocol, or what is also called the Aloha protocol. It was originally developed to connect terminals on the distributed campus of the University of Hawaii to their main computer in Honolulu. Hence, that's the name. I mean, Aloha is a word that says hello or even goodbye in Hawaiian. So that's the origin of this word. So this sounds like a very odd and a strange scheme. I mean, why would I want to just transmit and pray? Why not do something smarter? We cannot do something smarter. We cannot do something smarter because of the structure of the network, because of the properties of the network. That's something that I established earlier. So then, given this, what looks like a very strange scheme, the question to ask is, how bad does it get? Frankly, it doesn't. I mean, you can quickly do an analysis and show that it doesn't get as bad as we think it is. If it is total chaos, does it really become that much of a chaos? So the way to think about it is, I'll give you an analysis of that later. There is two versions of this protocol called the slotted Aloha, where time is divided into frames and you start transmitting only at the beginning of a frame. And there is something called pure Aloha, where anybody who wants to transmit at any time, there's no synchronization of clock or anything like that. You just transmit. Now, I'll just give you a quick analysis of Aloha. This is not very hard. You take this notion of a slotted Aloha. Assume there are n nodes, each of which wants to transmit in a slot, and they will transmit with some probability p. So the probability that there is a successful transmission in a slot is the probability that exactly one of those n nodes attempts a transmission, and the other n minus one don't attempt a transmission. And it doesn't matter who attempts the transmission. So if you take that and apply very simple probability principles, you will see that the probability that in a slot that there was a successful transmission is n times p times 1 minus p to the power of n minus 1. It's very elementary. You don't have to worry too much about it. Just trust me on this now. Now, typically you can say that p is a design, n is a given because that's a total number of nodes in the network. So you have to design p. So what is the best choice for p? The best choice for p is the p that maximizes this quantity, p success. Okay, the rate at which packets can get successfully transmitted on the wire. And differentiation equating to 0 and solving for p will give you that p should be equal to 1 over n. And if you substitute that in the expression for p success, you get 1 minus 1 over n whole to the power of n minus 1. And if you make n large, so the question to ask is, as n becomes large, does it become very bad? No, it doesn't, because as n becomes large, this number goes towards 1 over e. Okay, that's sort of a very happy ending, because 37% of the time you can have successful transmissions going. So if the total required rate on the network is 0.37 by n packets per slot time, then Aloha is a perfectly fine protocol. And many of the early applications did not require more than that. So the lesson from here, and this is the only math I'm going to use, the lesson from here is that if there is some randomness in the system, okay, simple protocols like this can actually make it work if there is sufficient over-provisioning of the resources. Meaning, instead of having 1 over n, you lose about 63% of the bandwidth. But but if you try to coordinate, you might actually end up spending more, and a lot more things can go wrong. Okay, so it's better to have something simple that works, although you have lost a little bit for what seems like a little bit of efficiency. Now, I mean, I leave this question to you. If I don't have these slots, does it get better or worse? Yeah. Now, a variation of this is what is called a carrier sensing protocol. So Aloha was designed for what I said was large propagation delay networks where the channel state is not immediately available. Okay. So in radio networks over small areas, channel state information is available. So because when I transmit, see what I hear on the channel is something that happened not very long ago. So I can assume that I know what is happening on the channel. Okay, so in this case, we can, although we can know what is the state of the channel before I start transmitting, I cannot know what is the state of the channel after I start transmitting. For example, if two nodes start transmitting simultaneously, okay, neither of them will know that another fellow has started transmission. Okay, so what you can do here is you can do one more improvement over the basic Aloha network called listen before talk. That means you sense the carrier, sense the channel before you begin transmitting, and start transmitting. Now, the formal name for this is carrier sense multiple access. And the idea here is just before beginning to transmit, you listen to the channel. So if there is an ongoing transmission, postpone the transmission. Otherwise, you just continue with your transmission. Another variation of this for wired networks was what was called CSMACD, where you should listen while you are transmitting. It is possible in small wireline networks. So, and if collision is detected, so collision is when two nodes are transmitting simultaneously on the channel, you stop the transmission and retry later. So now there are various other technical terms here. I'm not going to go into the details of the protocol performance issues, but this protocol is called CSMACD and it is standardized in the Ethernet. Now, what you can show is that every time there is a collision, you don't really lose too much bandwidth. If the propagation delay is small, every time there is a collision or when two people transmit simultaneously on the system, on the channel, it's only this much amount of, this 3 times the maximum propagation delay is what is the time lost on the. So if you can minimize the number of collisions, you're going to do very well. Okay, so so this can provide a significant improvement over the CSMA protocol. And just to give you a little bit of the Ethernet history, it began life as life as a 3 megabits per network, 3 megabits per second network at this facility called Xerox PARC, and this was around 75. And as soon as that happened, a couple of companies realized, in addition to Xerox, realized that there is an enormous potential. And this was a very interesting combination of three different types of vendors. Okay, there is a computer company called DEC. Many of you may probably don't know it. Some of us who are Some of you who are of my age would probably know a little bit more about it, VAX 11 and so on. That came from this company called DEC. Then there was Intel, which is the chip maker, which I guess everybody knows, and Xerox we all know. So these three together, they published a standard called the Ethernet standard. It was an industry standard, and there was no standards body that underwrote it or that agreed with it. Okay, so what they used at the time was a 50 ohm coaxial cable, which many of you may not have seen, and then they used a 10 megabits per second data rate on that, and they said the maximum size of the network, that means length of the cable in the network, would be of the order of 2.5 kilometers. It was reasonably good for medium-sized campuses. So after another 4 years of battle, and as soon as three companies started endorsing it, there were rival companies available at the time. For example, there was GM, which wanted to use it for automation, so factory automation. There was IBM, which was a very large computer manufacturer. There was AT&T, which was a large communications company. A whole lot of other companies were involved, and they did not want to give the leadership to DEC, Intel, and Xerox. So they wanted to have control over this, and they urged IEEE to sort of come in and start and standardize a protocol for local area networks. And they argued that Ethernet was just one of the many contenders. Okay, there could be other protocols. In fact, after a lot of fight, the IEEE agreed to have three separate parallel protocols. Okay, for those of you who are familiar, it's 802.3, 4, and 5. Okay, 4 and 5 essentially faded out, and only Ethernet stayed. And the idea here is to say that, look, even though you have an idea, a very good demonstrated idea in 75, for industry to be able to accept it took 5 years, and for a standard to develop with a lot of fighting, it took another 4 years. So there's a 10-year gap between an idea being ready in the lab, demonstrated and demonstratively ready in the lab, to it actually being used in practice is a 9-year gap. I mean, that's something that you might want to just sort of mull over when you look at how things evolve. And things have become a lot harder now, with too many more players fighting for every piece of the pie. Now, with respect to Ethernet, there are many more versions that have been introduced. They came up, and the latest one that you're familiar with would be 100 Mbps and gigabit Ethernet over what is called Cat6 cables. And the topology is not like what it used to be before. So we actually have what are called Ethernet switches. That was actually a no-no when it was a big taboo with respect to designing a local area network protocol when it was first introduced. It was just a cable, a passive cable running through the institution. So those days are over. It is now a fairly, an active network with a lot of wires coming into a wiring closet and so on. There are also 1 Gbps and 10 Gbps fiber optic links that are widely used in data centers. Okay, so that's about the background to multiple access networks. Now let's get to wireless networks, and let's see how regulation plays a role. Regulation here, I mean the law of the land. Okay, so what does the law of the land here mean? So now, before I get to that, I think I want to give you a sense of, just to give the abstraction of how wireless communication is done. So you have what is called a baseband signal. Okay, so a bunch of waveforms you design to communicate data at a certain rate. Okay, so there are waveforms. So these waveforms correspond to what is called the physical layer communication, physical layer specifications. Now, the way in which wireless communication happens is that you take this baseband signal and place it in some part of the spectrum or the electromagnetic spectrum, and through a process that we call modulation. Okay, so this sort of moved. So there's a baseband signal which is moved to a part of the spectrum, and what part of the spectrum you want to move depends on the application. So now different bands have different propagation characteristics, and what determines a propagation characteristic? The different molecules in the air, basically. Essentially, water absorbs some frequencies, some other molecules absorb some other frequencies, and so on. So depending on the environment, different wavelengths or different parts of the spectrum have different propagation characteristics. And depending on the propagation characteristics, you define uses. For example, there are separate bands for AM and FM. there are separate bands for there's a separate band for on-air TV. There's a separate band for CB radio. There are bands allocated for military use, for satellite communication, cellular telephony, Wi-Fi, etc. Okay? These bands are determined by the propagation characteristics in the band. Now, who makes this determination? It is actually the government agencies in a country and an intergovernmental agencies called the ITU. These together determine which band is used for what purpose. Okay, here are some example bands. Okay, so example sort of issues. So some bands are reserved for government and military use, and other bands are reserved for use such as AM radio, FM radio, etc. As I just said. Yeah. So these are some same things that I just said. So the key thing to take away here is that in this set of allocations that are there for every band, there is a small band called license exempt band. So in that, you don't need to, for every other band, you need to ask the government permission to transmit in that band. So in this license exempt band, you don't need. So every government has agreed that there is some part of the electromagnetic spectrum where you do not need licenses to transmit. So these are called license exempt bands. Okay. Yeah. Now, even if you are transmitting in a license exempt band, there will be some restrictions in terms of the power with which you can transmit and so on. Okay. So what does limiting the power mean for those? I mean, it's not very hard to see that if I limit the transmission power, the range of the signal gets limited. Okay. Now, cordless phone, for example, I don't know if these are useful anymore. I mean, these are from my time. I don't think cordless phone is being used by too many people anymore. So that, for example, has a 30 meter range. Okay. Now, second restriction is that it requires the use of a spread spectrum technique. I'll explain that a little later. So if you're using a license exempt band, you have to use spread spectrum techniques. The idea here is to spread the signal over a wide frequency band so that you don't get affected by the ambient noise all that much. Rather. There's a certain way in which this happens. Yeah. Now, let's, okay. The reason I brought this up is that 802.11 is actually defined in the license exempt band. Okay. So which means that you want to innovate anything, you want to deploy a Wi-Fi, you don't really need a license from the government. That's sort of the first sort of takeaway from this part of the talk. Okay. So meanwhile, if there are any questions, I can take them. Otherwise, I'll get to 802.11. Are there any questions?
Go ahead, sir. We will have the.
Okay, we can have questions at the end. Sure.
Yeah.
Okay. So 802.11, I'll just give you a quick picture for 802.11. Okay. Sorry. Okay, so roughly, I mean, what are the issues associated with 802.11? Again, if you have taken a networking course, this is something that you will see. You imagine there are three separate nodes here, A, B, and C. I mean, just to give you an example, A has a range determined by this blue circle here. B is not important at this time. B is within range of A. C also has a range which is sort of the empty circle, and B is also within range of C. Okay, now if let's assume that both A and C want to transmit something to B. Okay, so B is within range of A, C is within range of B. Sorry, A is within range of B, C is within range of B. So let's assume now that A is doing a transmission to B, but A's transmission is not heard by C. Okay, so if it wants to transmit something to B, it does not know that B is already receiving something, and it can start simultaneously transmitting to B. When that happens, whatever was being transmitted from A to B is lost, because two separate transmissions reach B at the same time, and it cannot distinguish between them. That's what is called a collision. Now, the reason for this collision is that C cannot hear A's transmission. Okay. Now, so C is what is called a hidden node with respect to A, and A is a hidden node with respect to C. The same thing could be happening in the other direction. So there's a second phenomena called exposed nodes. Imagine the similar situation here where B is transmitting to C. Yeah, B is transmitting to C, and A is hearing the transmission. Sorry, no, B is transmitting to A. Sorry, B is transmitting to A here, and C is hearing the transmission from A. Now, if at the same time, if C wants to transmit to D, D is not hearing B's transmission. So C could actually send a transmission to D, and D will receive it perfectly. But C, because it is receiving B's transmission, does not know that the channel is free. It is capable of transmitting a signal to D. It does not know that. So it is just exposed to a transmission from B to A and is losing an opportunity to transmit. Okay, so it wrongly assumes that the channel is busy when the channel is perfectly fine. Okay, so this is a lost transmission opportunity. In the previous case, the hidden node sort of messes up an ongoing transmission because it could not hear it. In this case, a signal that it need not have heard is preventing it from transmitting to another node. So this is what is called the exposed node problem. Okay. Now, to prevent this, what CSMACD does is that it follows a 4-step protocol, okay, or a 5-step protocol. The first step is as follows. Now, when there is a node A, in this case I have a node B, sorry, that wants to transmit to anybody. It doesn't matter whether it is to C, or let's assume it is transmitting to C. Okay, it first sends something called the request to send signal. Okay. So now whenever a request to send signal is transmitted by B, it is received by both C and A. Okay, so, and if it is B is requesting C for permission to transmit, asking C if it is free. Okay, if it is free, then C will say, yes, you can go ahead and transmit. So that is called the clear to send signal, the clear to send control signal. Now, when that is ready, then B will transmit to C saying, I'm about to send you data. So that is what is called the DS signal. Now, mind you, when RTS is heard by A and CTS is not heard by A, then A knows that there is a transmission going on, or there is a transmission attempt happening. So it will not initiate a transmission. And then when B says DS, essentially saying I'm about to send data to you, to C, A knows that a data transmission is about to begin. And then a data transmission begins, and when it's all over, C sends an acknowledgement to B and says, okay, now this whole transmission is over. Okay? So you can see that A is the hidden node, and D is in some sense, D also gets some information about. Okay, now let's look at A and D as to what happens. When at A, it receives an RTS but does not receive a CTS. So what does this mean? It means that it knows that somebody's attempt, and then it also sees a DS, which means that there is an ongoing transmission, okay, which will last up to this point till the end of that transmission and the acknowledgement that follows that. It will last till that, so it has to keep quiet. So it should not disturb a transmission that is being received by B. Okay. Now, what happens at D? At D, it also knows that it heard a CTS but did not hear an RTS. If it heard a CTS, that means that C, somebody within D's range, is trying to receive a packet. Okay, so now it knows that it has to wait till acknowledgement is received to know that somebody within its range is now receiving a packet and it should not disturb it. So D will not transmit when C is receiving because of CTS and ACK. A knows that a transmission has begun, okay, but because it has not heard the CTS, it knows that it is potentially just an exposed node and it can begin transmission to somebody else, but not to D. Okay, it should not disturb a B's transmission. Basically, that's all it knows. But if it is not disturbing a B's transmission, it can transmit to somebody else. But what is important here is this whole sequence of message exchanges. You can see that there is a part that starts with an RTS, a CTS, a DS, and then there is data. Okay, and then there is acknowledgement. So just to send that small piece of information corresponding to data, there's a whole bunch of messages that get exchanged. Okay, so that is what I want you to take forward to the next part of the discussion. And mind you, because we do not know what is the channel conditions between B and C, all these control signals have to be transmitted at the lowest rate. So it takes a lot of time, okay, as opposed to the data packet. By that time, the channel conditions have been assessed. So the data part can happen very fast, but the preceding control signals will take a long time. I'll show you some more pictures about that. Okay. Yeah, so this is basically a summary of what I just said. So there are control frames that are exchanged before actual data transmission. Okay, so this exchange informs all nearby nodes that a transmission is about to begin. Okay, this is just the summary. Sender transmits an RTS frame to the receiver. the RTS frame includes variety of information about the impending transmission. And yeah, receiver will reply with a clear to send, which is a send, and tells the RTS saying, okay, you're fine sending this particular packet, and the information that is contained in the clear to send is also available to others within the range of the receiver. Okay, yeah. So the nodes that see the CTS frame know that it is close to the receiver and therefore cannot transmit for the period of time it takes to send a frame of the specified length. And any node that sees the CTS frame but not the RTS frame knows that it is not close enough to the receiver to interfere with it, so it is free to transmit. Okay, so this is sort of the basic protocol of the 802.11. And receiver will send an acknowledgement after successfully receiving a frame, and all nodes must wait for this acknowledgement before trying to transmit. Yeah, so there are collisions that can happen and so on. I'm not going into the details of the collision because that's a fairly more elaborate discussion, so I'll skip that part. Okay. So although I have slides, I can come back to it for those of you who are interested. Okay. Now, so if you keep that in mind, so what has happened to 802.11? Okay. So like Ethernet, 802.11 is designed for use in a small geographical area. So for those of you who know, if you go too far in your house, 802.11 signal dies away. Okay. Now, it also supports many additional features like power management. Okay, it's important especially in a wireless node. It also has a lot of security mechanisms. Again, I'm not going to go into the details of this. Yeah, so I would urge you to understand that many of you may have already programmed your Wi-Fi interfaces with a variety of these options, so you would know some of these things. Okay. Now, so the original 802.11 standard was what was called the legacy mode. And what it did was it defined two physical layer standards running on 2.4 gigahertz band. Now, this is, remember I said that a wireless signal has to be placed in a particular band. And in this case, the license exempt band was available in 2.4 gigahertz. And the technology to transmit at reasonable rates around the time that 802.11 became a standard was available in that band. Okay, so the early data rates were of the order of 2 megabits per second. Okay, this is, I'm talking of circa early 1990s. And there was frequency hopping spread spectrum. Mind you, this is a license exempt band, so you have to use spread spectrum techniques. So there was frequencies hopping over 79 1 megahertz wide frequency bandwidths. Okay, and the direct sequence, there were two spread spectrum techniques used. One was the frequency hopping spread spectrum technique and a direct sequence spread spectrum technique. The direct sequence used 11-bit chipping sequence, whereas the other one used 79 of these bands. So essentially in frequency hopping, you randomly go from one band to the other. The random hopping, so only the transmitter and the receiver know the actual sequence of bands that you will be traversing. For everybody else, it looks like noise. The same goes for direct a similar notion for direct sequence, where one bit is transmitted as a particular 11-bit pattern. Okay, and 1 and a 0 are transmitted as particular 11-bit patterns. For everybody except the transmitter and the receiver, everybody else sees it as noise. So using some correlation techniques, you can extract the bits from this chipping sequence at a receiver. Yeah, so this is sort of a quick overview. Transmit signal over a pseudo-random sequence of frequencies. Receiver knows the transmitter's random sequence because it uses the same random number generator and is able to correctly receive the frame. Okay. In direct sequence, each bit of a frame is represented by multiple bits in the transmitted signal. And for each bit, the sender actually XORs that bit and the n random bits. Each of these bits is what is called a chip. Yeah, I'll skip this part, and these are pictures for that. So what is important here is that after the basic one, there was a standard called 802.11b. Now, this was released in 1999. And it now from 2 megabits per second, we moved to 5.5 and 11 megabits per second using a high rate direct sequence spread spectrum. Okay, so I've just told you what a spread spectrum is. The same thing is done here. Okay, yeah, so there was also, so this is the, okay. The other thing about this was that there were there were about, I think there were 14 channels. Yeah, there were 14 channels that was available for use. Mind you that in the same area, multiple access points could be residing, multiple wireless networks could be residing. So to be able to separate them out, you had 14 channels. Each one had a 22 megahertz bandwidth. But the difference was that these channels were not non-overlapping. Okay, they were overlapping in the sense that the channel number 1 and the channel number 2, the non-overlapping part was only 5 megahertz. Okay, so there was a combination of DSS and the channel separation of this order would allow multiple WLANs to coexist in the same geographical location. I mean, for example, you could see that. I mean, your and your neighbor's Wi-Fi coexist. So some trick like this, because of these, they're allowed to coexist in the same place. Okay. Now, yeah. So then, okay. So the key takeaway here is that the only thing that changed from the 802 basic 802.11 to 802.11b was an increase in the data rate. Okay. So what was a 2 megabits per second network became a 5.5 megabits per second or 11 megabits per second network. Now, how do you determine what you're going to use? In fact, what will happen in many of these is that because you're going to allow a larger range, what will happen is that there could be nodes which are the channel between them, it may not be of a very high quality. So if the channel is not very good, you cannot really transmit at 11 megabits per second. You will have to drop down the rate. So the standard will actually define a large number of intermediate values or intermediate data rates. So 11 is the peak, but other data rates are also feasible. Okay, so meaning other lower data rates, 5.5 is 1, and it goes further all the way up to 2. So the 11 is available only when the channel is very good, and the others are not available when the channel is not very good. Okay, so what that means is that if I'm sending a 1000-bit packet, okay, the amount of time that I occupy a channel can be very large. So if there is a network with, a node or a node pair, a transmitter receiver pair with a bad channel coexisting with a transmitter receiver pair with a good channel, then everybody suffers, because when the bad channel pair gets the network, it is going to use the network for a very long time. Okay, remember that only one person can use the network at any given time. So it is going to use it for a very long time. So that sort of limits the performance. And that's something that you have to remember when I discuss the next part. Okay. Yeah. Now, yeah, the next improvement was again only in the physical layer. Okay. So they introduced a new physical layer technique, essentially how to encode the bits and increase the data rate on the physical layer channel. They went all the way up to 50. This is 802.11a and g. They went all the way up to 54 megabits per second. Okay, and the way in which this was done was using what is called orthogonal frequency division multiplexing. In orthogonal frequency division multiplexing, what happens is there are multiple carriers. Okay, in this example, there are 52 subcarriers in a different band, in the 5 gigahertz band. Now, what you will do is you will try to see which of these subcarriers you can use. So, and you'll use as many of them as possible. So there is a negotiation between the transmitter and the receiver as to which subcarriers are being used and at what data rate. So that gives you the overall data rate. So there's a fairly complex map of the bit rate to the subcarriers that you're going to use, which is negotiated upfront when the source and the transmitter and the receiver sort of set up a communication channel between them. And that is what is used to obtain a higher rate. Because of OFDM, what that means is that there are different frequencies will have different noise characteristics. Okay, so in the same place. So it is possible that you can combine a large number of these subcarriers to get a fairly large bandwidth or large part of the channel. So this is what was used to be able to sort of, if the whole spectrum, the whole band is bad, then you will not be able to, only if parts of the band is bad, then the transmitter would not be able to use the whole band. So if you now break it up into smaller pieces, you will find out which part of the spectrum is good. So you'll start using that. Essentially, I mean, intuitively, that's all that is being done here. Okay, so each carrier is modulated now. Now, as I said, there is the association. There is the choice of the subcarriers associated with OFDM, and then inside each carrier there are modulation techniques, and there's a waveform. And how many bits does each waveform represent? BPSK means it represents 1 bit. QPSK is 2 bits. 16 QAM is 4 bits. 64 would be 6 bits. Okay. So again, your ability to encode depends on the quality of your modulation and the quality of both the transmitter and the receiver. Okay, so people have improved these techniques sufficiently. So the increase in the data rate is achieved by a combination of higher, better modulation schemes and OFDM. Okay, and then there is also coding rate to, again, I won't go into the details of this, an improved coding schemes to ensure that that the received, the errors are minimized. Okay, but the interesting thing here also is like before, although 54 is the maximum data rate that is that it can support, if the channel is not very good, you can go down all the way up to 6 megabits per second. Okay, and I'll reiterate what I said earlier, that if a good channel pair, if a good channel transmit receive pair coexists with a bad channel receive pair, both of them suffer, because one fellow will hog the channel for a very, very long time, for every time that it gets the transmit. Okay, so here are some more details. Again, all the details are not very critical, but the takeaway from here is that there are so many. There is the physical layer has been improved substantially to provide increased throughput, but the quality of the channel the combination of the qualities of the combination of the channel qualities of the various nodes that reside in a given area determine the experience of everybody. Because as I said, if somebody is coexisting with a bad channel, then the bad channel, every time it gets to transmit a 1000-bit packet, it takes a long time compared to, for example, the 48 megabits per second source destination pair. Okay. Now, how far can you go with phi? Okay. Yeah. So now a key thing is that if you improve the data rates, you need larger bandwidths. And if you need larger bandwidths, you cannot operate at lower carrier frequencies. You have to go to higher carrier frequencies. And if you go to higher carrier frequencies, the propagation characteristic of the higher frequencies is such that you really cannot go very far. Okay. So if you go to higher frequencies, the operational distances come down. Okay. Yeah, this is APs, higher densities of APs. Now, another thing that happens is if you start increasing the physical data rate, remember I said that there is a control part of the transmission, the RTS, CTS, DS, and then there is an ACK. There are 4 parts plus the data part. So there are 5 parts, if you will, of which only 1 is a useful part. Okay, useful in the sense of contributes towards the throughput. The others are necessary. They're not. You cannot do away with them, but you have to live with them. But you have to know how to live with them. So now, yeah. So there is also many times if there are collisions, so there is also back-off durations and so on, which is determined by what is called the slot time. Again, collision window and the slot time. Collision window is determined by the size of the network, and slot time is determined by the minimum data rate that is achievable or that is allowed in that area. Okay, there are some more terminologies which I'm going to skip, but here is a good view. Okay, so this is not my figure. This was also taken from another source. I have not written down the source, but it's available fairly widely. Okay, now when I'm transmitting, when a node is transmitting, what you are going to see here is that it starts at, I'm not sure if I'm able to show this here. Let's see. Oh, okay. No, I can't point to anything. Yeah, let's see. Yeah, the point at which, this whole part on the top part of this figure. Okay. Yeah, I can't show anything more. I can't point to anything, but anyway, you can see what I'm trying to do. You will see that there is this long part here where there is something called the DIFS. Then there is a whole bunch of potential backoffs because it probably collided, etc. Then there is a preamble. So this is a preamble is for the transmitter and the receiver to synchronize their clocks. PLCP header is to provide some information about the kind of modulation schemes that they are going to use. Then there is a MAC header, much like the Ethernet header. Then there's an actual payload where this is the part that is being transmitted, the data that is being transmitted from the source to the destination. Then there is a checksum to make sure that the packet is correct. Then there is a gap, and then there is an acknowledgement. Okay, and before all this, there is this whole bunch of other control information that is being transmitted. Now, all of this takes up, and mind you, the other thing that you have to remember is that all of these, other than the dark blue part, especially the light blue part, has to be done at low data rates, because you want to be sure that this was received correctly at the destination. Okay, so because of that, if you can see, the light blue part is the overhead, the dark blue part is the actual payload. So the overhead is substantial compared to the packet. So one trick that you can think about using is that because your overheads are so large, every time you get the channel, don't just transmit one packet, transmit a large number of packets. So that's sort of something that's obvious. Instead of, so another way to improve throughput, there are essentially two trajectories to improving the throughput. One is to improve the physical data rate. The other is that you also reduce the overhead. So that means every time you get a packet, you get the channel, you amortize the overhead associated with this channel acquisition among a large number of packets. Okay, that's sort of the key takeaway from this particular slide. Okay, I won't go into the details of this, but here again you can see something interesting. The top part corresponds, the numerator here corresponds to the useful time spent on the channel, and the denominator corresponds to all the sources of all the overheads. So as you increase the what is called the payload size, the amount of packets amount of bits that you allow in the so-called dark blue part, the throughput, the maximum throughput that is feasible will behave in this manner. Okay. Again, I'll skip the details of this, but it gives you a sense of what will happen if you keep the payload size constant. Okay, so if you start increasing the payload size, the efficiency of the system will start improving. Okay? So yeah, so just to summarize what I was just saying, your overheads are almost fixed. So increasing effective use per channel acquisition is what you need to do. So the way you can do that is to have large data frames, but there are prices to pay. So if you make the data frame very large, you can cause packet errors. Okay, so I mean, you can sort of, even under a good channel, the packet error probability grows fairly fast. Okay, it's at least linear, if not more. So you cannot have very large data frames, because that can lead to increased error probabilities. Okay, so what you can do instead is to sort of, every time you get the channel, you make multiple small frames. Okay, so this is what is called frame bursting. Okay, so for every channel acquisition, you transmit multiple frames, and so this helps in traditional traffic patterns. What do I mean by traditional traffic patterns? If the AP is the dominant sender, then access point will get. So most of the cases, if you look at the way in which you use your Wi-Fi, you are usually downloading something. Everybody in the house is sort of downloading something from the AP, from the access point. So this is once the AP gets the channel, it is going to transmit for a large amount of time to a potentially large number of users. Okay. Another, so the way in which this is done is essentially what is called frame aggregation. And so you divide, so the first part here, if you look at the bottom of this figure, PHY header and the MAC header is what we had before. And inside the dark blue part, you have actually expanded it significantly, where instead of one data unit, you have put a large number of small subframes. Each subframe is like the old packet. Okay, so we have n subframes in this particular example, and you can so you aggregate what is called a MAC service data unit. The physical layer header is amortized in this case, and data packets to be sent to the same receivers are concatenated. The total number of bytes in that dark blue part can be of the order of 7,009, almost 8,000 bytes. Okay. Now, the question also is, what happens to the sender? Does it have to wait till it can send up to 8,000 bytes, or does it send as soon as it? I mean, what is the protocol that the sender should use? So that's another sort of a small design choice that people make. And there are, again, it's a fairly standard question, and people know how to answer these. Okay. Now, the questions to ask in this case is, should you send it to one destination or send it to multiple destinations? Do you aggregate at the physical layer or the MAC layer? Okay, so for example, when I say physical layer, when I say MAC layer, what I mean is that I have to send it only to the same destination. Okay, when I aggregated the physical layer, I could access the channel and use the same channel to send it to multiple destinations. The other question is that if there are multiple destinations, the data rate could be different. Should I use the same data rate or can I use multiple data rates? Again, mind you that when I start doing this, things can become very complicated. Okay, so I'm not going into the details of this. I'm going to sort of expose you to the problems that one needs to address. Okay. The last question, or one more question to ask, is that what happens when do you acknowledge? Does the transmitter acknowledge as soon as it receives a packet, or does it wait till all the packets are received to acknowledge? Okay. So then there is something called SIFS, which I have not introduced as part of this course. So that's another thing that needs to be used. So the additional features in what is called 802.11n is that it can go up to 600 megabits per second. Channel widths of 40 megahertz, coding rates of 5x6. Again, these are not important. Yeah, so this uses aggregation techniques of single MAC header and a checksum. It also has aggregation technique of single phi header and separate MAC plus checksum for every PDU. I think I'm running out of time. So I'll quickly give you an overview of, I'll skip all of this, the motivation for the new generation of Wi-Fi, and give you this picture, and I'll leave you with this picture as to how this is evolving. Okay, so Wi-Fi 6 is 802.11ax. 802.11ax, it is trying to improve the performance through multiple ways. Okay, so these are the four sort of axes which it uses to improve the performance. One is spectral efficiency. So what does spectral efficiency mean? That means in a given spectrum, I want to pack more bits per second. Okay, there are three techniques that are used. One is improve the modulation scheme by using the 1024 QAM. Use MIMO. The antennas are made much better. Antennas and the receivers are made much better. And in this case, 8x8 MIMO. And then use longer OFDM symbols to improve the spectral efficiency. So that's another one trick. The other trick is to allow for high density. I mean, it is expected now that there will be a slightly larger range. And because of the larger range, there could be more nodes that are using Wi-Fi. And this Wi-Fi, the Wi-Fi Wi-Fi AX or Wi-Fi 6 is supposed to be usable by a diverse set of requirements. So which means there are a large number of different types of devices who will be using it. So there will be high density of users. So use OFDMA, okay, and try to use some kind of a spatial reuse. It has a higher channel, the higher band, the 6 gigahertz band, which means it allows for a larger bandwidth of the channel. And it also allows longer ranges. Okay, so if you have if you want to expand the size of the network, if you have a long range, then the error conditions, etc., can be much larger. So you have to use different modulation techniques. All these different modulation techniques are being used. And more importantly, you have to have some power saving. I mean, now, with everything going wireless, you have to have some power saving schemes built into the protocol. So 802.11a6 takes care of some of those things. Okay. Again, I think I'm running out of time, so I'll probably not go into too much details of this. I'll just give you this last this thing. Yeah, so in 802.11ax, channels are allocated over time and frequency organized on a per frame basis. Okay, so as I said, mind you that OFDM means there are frequencies, different carriers, and you have to allocate who takes which carrier, which node takes which carrier. So that allocation is done in some centralized scheme on a per frame basis. Okay, I think these are sort of, many of these terms I have not introduced, so I'll have to probably skip them. Yeah, I think I'll skip many of these things. This is probably doesn't work. Yeah. Yeah, I think this is probably the last slide. So several QoS features are also incorporated into this to allow for low latency requirements and bandwidth reservation. 802.11ax is turning out to be a fairly sophisticated local access network protocol, okay, or a wireless access network protocol. There are also several power saving techniques. There are many standards that are still in the making, and people are actively, vigorously participating, including some of my colleagues here, on many of these standards bodies. And people are already starting, although Wi-Fi 6 is not ready, so people are already talking about Wi-Fi 7, much like 5G, 6G, and whatever else G there is. Okay. Yeah, so that's sort of, that's where I conclude. If there are any questions on any parts that I missed or I didn't miss and you want me to cover, I'll be happy to take any questions right now. Thank you very much.
Thanks a lot, sir. It was a very good lecture, mainly on communication network. There are many EC students over here who are currently studying communication networks, and you have given a brief history about the protocols, what we have used, also the emerging technologies, what they can include in their projects. So thanks a lot, sir. I request our student Akash to take over the Q&A session.
So thank you, Nandini ma'am. Very good evening, sir. Thank you for giving us this lecture. And we have a few questions, and I'll name them one by one, and you can answer. So the first question we have is about the Starlink project and your input on that.
I have no idea what it is. What is it?
So it's the SpaceX satellite constellation that's supposed to give internet.
I have no idea what Elon Musk thinks about or what he wants to do in life. Sorry, I have not followed that at all. Sorry.
That's okay, sir. And we have another question about how we can reduce attenuation and the modern techniques for the same.
What do you mean attenuation? Signal attenuation.
How we can reduce it? Yeah, signal attenuation. How it can be reduced using modern techniques.
Yeah, signal attenuation is a property of the channel. Okay, that you cannot change. What you do is you address it. You address it by designing suitable waveforms, physical layer waveforms. Okay, and using techniques like MIMO and OFDM. Okay, what does MIMO do? MIMO. Okay, let me give you both. What does OFDM do? OFDM says, look, there are. I mean, just to give you an example, this is not a real example, but just to illustrate, it's an illustrative example. There are 6 carriers. Okay, sometimes carrier 1 will be good, sometimes carrier 2 will be good. Okay, so I'm going to use the carrier that is good at this time. So mind you that attenuation is a channel characteristic, which is a random process. Okay, so there is a randomness in the channel, and you continuously monitor the different channels. Okay, let me see if I can show it to you on a picture. Okay, something silly happening here. I'm not able to. Okay, just 1 second. I can't even stop sharing. Okay, something. Okay, I'm not able to see my mouse. I don't know what's going on. But anyway, so roughly this is how it happens. Okay, so let's assume there are 6 OFDM channels, right? So if there are 6 OFDM channels, I will, and there are 2 separate users. Okay, 2 separate pairs of transmitter receivers. So if there are 2 separate pairs of receivers, I'll keep monitoring for both of these pairs. Let's assume there is a central entity. Let's assume God for now. Okay, so God is monitoring both of those channels. Okay, and finding out which combination of these subcarriers is good for both of them, and God will look at it and keep allocating them. That's one way to do it. Another way to do it, and you can use both of these techniques simultaneously. Another way is what is called MIMO. So what does MIMO do? MIMO says that there are multiple transmit antennas and multiple receive antennas. So let's assume there are 2 transmit antennas and 2 receive antennas. Okay, so I can send out 2 separate signals. The receiver, both antennas are going to get 2 separate signals. So there are a combination of 4 signals available at the receiver. Each of these 4 has taken a different path. They had a different characteristic in the beginning, and they had a different path. So now you have 4 signals. Hopefully not all of them are bad simultaneously. Okay, so if you understand channel behavior a little bit, you can design these 4 signals such that not all of them are bad simultaneously. Okay, I mean, again, I'm being very, very glib and crude here, but that is sort of the intuition. Okay, so I can receive from each of these 4 channels. Now I process and then determine what was the bit transmitted. So I can improve my spectral efficiency because of MIMO. And improving spectral efficiency means combating attenuation. Okay, attenuation cannot be combated. It has to. Attenuation cannot be eliminated. It has to, you have to learn how to exploit it, how to work around it. Okay.
Thank you for that answer, sir.
Yeah.
We have another question from Anil. He asks, what are the challenges in designing new network architectures capable of handling dense and adaptive wireless infrastructure?
So the biggest problem has been simultaneous use. I mean, among the many problems are simultaneous use. Okay. So if I'm in the, if I have one channel, okay, one channel to use, and if there are 100 people wanting to use the same channel simultaneously, I have to divide the capacity of the channel among 100. Okay. Now, one way to address that is use what is called spatial reuse. Okay. What do spatial reuse? I'm going to use, you pick up a pair which is in one part of the geographical area, and pick up another pair of communicators in another part of the geographical area, and ask them to transmit simultaneously, hoping that they won't interfere with each other. Okay. So if you pick them carefully, that's exactly what will happen. And this is exactly what happens, for example, in your cellular network. That's called spatial reuse. I use the same resource in multiple parts, multiple geographical parts. Okay, so that makes it very simple. That makes it very easy conceptually. This is not easy in practice. Okay, I just want to. These are as I said, I'm trying to be glib and sort of crude in describing, but the intuition is just that making them work is a different ballgame altogether. Does that satisfactorily answer you?
Yes, sir. That was a pretty good explanation you gave for that question. We have another one from the same person, and he asks if there are any protocols for mobile devices to talk on multiple access points concurrently, and how will the design of the preamble vary for such a case?
The design of the preamble, I haven't, I am not aware of being able to okay. So this is another interesting, so let me say a technological, the evolution of technology. Okay. A big sort of selling point of 802.11 and Ethernet was that they're distributed protocols. Okay. There is no centralized control. Okay, so which means that you don't. I mean, nothing can. There is no central place where things can go wrong. They have slowly evolved. They're increasingly evolving towards a centralized system. Ethernet, you all know. I mean, when we first deployed Ethernet, there was no such thing as an Ethernet switch. There was no such thing as even a hub. It was just one cable running through. All you had to do was tap into it. Okay, it literally tap into it. So you had to just poke you had a needle, and you just poke the needle into the cable and suit it in a particular way. And if you got that right, you had network access. Okay, so there was no active component in the whole network, meaning there was no signal regeneration, no nothing. And then slowly, people found the centralized system more convenient because they knew how to manage it. The same thing is happening with Wi-Fi. Okay, to a large extent, things are getting centralized. So there is an access point or some kind of a centralized device which is controlling access to the network. Now, so talking simultaneously to two APs seems like it doesn't seem reasonable to me because of this control. I have to be associated with somebody, so I cannot do that. I mean, but if you have a very specific version in mind, for example, if there are multiple access points of the same enterprise network, then there is communication between them. I mean, then there is some kind of the two access points will be monitoring a particular node to see who wants to be associated with that and when to hand off and so on. Okay, so again, it depends on what exactly you mean by two access points. If it is from the same enterprise network, like for example, if you buy from Aruba or Cisco, not the one at your home. Okay, they are very different. The one in your home, if you buy two access points, they are two very different access points typically. But if the one in the campus, if you have bought it, if you have bought an enterprise solution, you will typically the access point will be monitoring each of these nodes to make sure who has to be currently picking up the signal from a particular mobile, exactly like what the cell tower does. Okay, so what you are transmitting is heard by both the access points. That's the way it is done. So simultaneously communicating with both is not something that I'm aware of. Whether there is whether there's an evolving standard or even an evolving application, I'm not aware of. Is there something more specific, I can probably look in and tell you. But under other circumstances, I don't know. I don't know the answer to that. Okay. Yeah. Hello.
Yes,
Yes, sir.
we
So
have a
there's-
last question.
We have one more question, sir.
Sure, sure. Yeah, yeah. Go ahead.
And it's asked by Shao. And the question is, could you briefly introduce us about the major difficulties of satellite network communication and how the technology can be applied to the field of satellite communication?
Which technology?
Satellite network communication.
Satellite network communication. Okay. I don't follow again that literature. Yeah, maybe I'm too specialized for. Yeah, I don't follow the satellite communication literature fully. But based on what I know, the biggest challenge is the propagation delay. Okay. If you look at so-called geosynchronous satellites, the propagation delay is 250 milliseconds both ways. So the round trip time is 500 milliseconds. That's a hell of a lot. Okay, you can't really have real-time communication. Imagine most of you must be playing some games on the network. Imagine trying to play a game with a 500 millisecond lag. There's no way you can do anything useful there. Okay, so the biggest challenge is that. I'm not sure if there's any other major challenge. I mean, technologically, these are all sort of approximately solved problems. In the sense that, you have to design more sophisticated antennas, more sophisticated, the physical layer techniques and so on, and the attenuation is massive. So the noise of the component can be comparable to the channel noise. All of that are probably pretty much what has been known for the last ever since Arthur Clarke said you can communicate using satellites. But I'm not sure if there's anything new that has emerged in that. I don't follow that literature, so I'm not totally aware of any of the new developments there. But just to give you a small example, there was an attempt made in the late 1900s, early 2000, to have what are called low orbit satellites. Okay, because if you put a geosynchronous satellite, the delays can be of the order of 500 milliseconds. Now, to prevent that, instead of having it at 36,000 kilometers, you have it a few hundred kilometers. Okay, hopefully that will ensure that the delays are not very large. I mean, there was a project called Iridium, which had this constellation of satellites around the Earth, where there would be these handoffs and fairly sophisticated scheme. But from what I know, it never took off. So I'm not sure whether it was just a technological failure of any kind or more a commercial and a market failure. I'm not very sure. But that is the only satellite communication I had sort of followed a little bit. Other than that, I mean, at least the satellite communication that is used, satellite communication for communicating between entities on the Earth, that is very different from satellite communication or communicating from the control station on the Earth, for example, the ISRO's control station to control signals to Mars. That's a completely different ballgame. And I have not followed that literature at all. So I don't know how those things are how different they are from the standard ones, except to believe that they provide a hell of a lot more protection, and the amplifiers and the components are probably a lot more, lot more robustly designed. Other than that, I can't think of anything obvious. But again, I don't follow it, so I can't tell you off the bat. Yeah.
Thank you so much, sir.
Yeah.
I guess
there are a couple more. I can take more. I mean, just since I'm here,
yes,
I can take a couple more if you need.
Yes,
There are
sir.
no more questions, sir.
Okay, very good.
Okay.
Thank you, sir.
Sure. Okay.
Yes, sir. Thank you so much. Again, I would like to say, I guess most of our students, they have asked questions on this, and it's actually very helpful. And the last question asked by one of alumni of our DSU. So even we are happy that he listened to complete session, and he had some interest in some satellite communication network. And yeah. So thanks a lot, sir, for taking over the session.
Thank you very much.
Yes, I request our Honorable Vice Chancellor, sir, to give a conclusory words. Sir?
Yeah. Good evening.
Good evening.
I think as a chairman of BITES, it's my profound duty to thank Professor Manjunath for taking time off his busy schedule to be with us to deliver a talk, which was very interesting, wherein it touched upon the entire history and evolution of Wi-Fi. Extremely useful. One thing that I realized is when we do not get Wi-Fi, we keep on worrying about it, and we, without knowing the kind of things involved. Possible this lecture would open up and make us understand what are the kind of the process involved in transmitting the data from one point to the other point. And this lecture was extremely useful because the Wi-Fi has become a part and parcel of the day-to-day life. The second, it has come from an authority who has a part of ERNET design in the country. I think he was part of ERNET design in the country. I think above all, Manjunath, a very simple person and easily approachable and extremely straightforward and also very unassuming. That's one very simple human being. That's what I like in Dr. Manjunath. I think when I approached him, and probably he could find some slot and finally come and talk to us today. Sir, thank you very much.
My pleasure.
And we request you to consider delivering few more lectures for BITES at a later point of time, whenever you are free. We will look
If
at
I
that.
have something
We look
useful,
forward.
I'll be happy to. No problem.
Yeah, sure, sir. Sure. Thank you. Thank you very much.
Sure. Sure.
Thank you, sir.
Thank you very much. Yeah.
I also thank all the participants for
Of course.
being a part of this lecture. I think this is a 15th or 17th lecture that we had in the series in the last one and a half months. And each of the lectures stand out in terms of the various aspects that we would like to cover and give information to our students and faculty. It was a good attendance. About 131 students attended, participants were there on the lecture, and close to about 100 to 150 were there on YouTube live. I think close to about 250 people participated in this particular lecture. Thank you very much, sir.
Thank you very much. Yeah. Thank you. Thank you.
Yeah. Thank you.
Yeah.
Thank you.
All right.